Yeah, very good afternoon. I understand we are online through the platform of YouTube and Facebook.
Janardhan, please confirm.
Please confirm.
Yes,
Okay, sir.
yes, we
You
are
can
online.
start.
Yeah.
Okay, so very good afternoon to all of you. Very good afternoon, Chairman ISRO, Secretary DOS, Scientific Secretary ISRO, Kiran Kumar Sir, Chair of Apex Board, former Chairman ISRO Secretary DOS, Director IIRS, esteemed directors of the ISRO DOS centers, units, autonomous bodies, academicians, scientists, teachers, and the students who all have joined from the social media platform as well as the platform of this video conference. Welcome to all of you. Today we have assembled here to mark the inaugural event of the ISRO START 2026 edition. This happens to be the fourth edition of this program. We started in the year 2023, and every year this START program has got one theme, and this year's theme is observation from space. And in this observation from space, there are 26 lectures which will be delivered by pan-India experts, including scientists and engineers from ISRO and many other institutions. And these lectures are designed for the non-experts to cover a very broad uh, overview of the subject in its entirety, covering not only the space-based astronomy, but also some premises of Earth observation and instrumentation technology and so on. So with this brief introduction, I am happy to call upon Dr. R.P. Singh, Director IIRS, for his welcome address. Over to you, sir.
Thank you, Dr. T.P. Das. Good afternoon to everybody. Respected Dr. V. Narayanan, Chairman ISRO and Secretary DOS, Sri A.S. Kumar, Kiran Kumar, Sir, Chairman Apex Science Board ISRO, Sri M. Ganesh Pillaiji, Dr. T.P. Das, Directors and Seniors of ISRO Centers, faculty member, dear participants, joining this inauguration session of START Program 2026 from the different parts of country, in fact, including all the states of our country. Greeting from Indian Institute of Remote Sensing, Dehradun. IIRS is mainly involved in training and capacity building of ISRO activities with respect to remote sensing and space science and technology. This program is a joint effort of IIRS Dehradun and Science Program Office of ISRO Headquarters, which aims to spread awareness of space science and technology in country. We are thankful to Chairman ISRO and Kiran Kumar sir for encouragement to carry out this online course and all the faculty members who has kindly accepted to deliver talk from different centers of ISRO and national institutions. This program consists of 26 talks from the eminent scientists covering fundamental concepts to the complex technology involved in the scientific observation of space. This program is unique in itself, and it is a part of many new initiative is being taken in space science education, particularly in this START 4 program. Also, this edition of START, we have planned to even call some of the students to IRS and make them to interact with the faculty members who will be teaching them. So I'm sure it is going to be very interesting to all our participants. My best wishes to START 2026 program. Thank you very much.
Thank you very much, sir, for having given a very good overview of the entire program and telling about the possibilities. I now request Scientific Secretary ISRO for the opening remarks. Over to you, sir.
Respected Chairman ISRO and Secretary DOS, Dr. V. Narayanan sir, Chairperson of Apex Science Board, ISRO, and former Chairman ISRO and Secretary DOS, Sri S. Kiran Kumar sir, Director SPO TP Das, and Director IIRS R.P. Singh, and other center directors and nodal center officials, my dear students and space science enthusiasts joining through YouTube and Facebook. So very good afternoon to all. So the Space Science and Technology Awareness Training, START. This was, as mentioned by TB Das, was initiated in 2023. And this year, the theme is observation from space. And as you are aware, there is a Space Vision 2040 and has been rolled out, and this is aligned with the Viksit Bharat 2047. And under the Space Vision 2040, we are having the launch of Bharati Antariksh Station, the Chandrayaan follow-on missions, and also the lunar landing missions. And all these scientific missions will the basic outcomes. There are two outcomes of the scientific missions. One is the technology which is required to achieve these scientific missions. The second part is the understanding of the universe and for understanding the universe in a better way, so for a better life on Earth. So, however, in addition to all this, there is going to be another section that is the most important one. That is the participants here, the young generation aspirants of the space science. You are the future stars, and who will take India to greater and greater heights as we progress in future. Now, the START program is attracting thousands of registered participants from diverse science and technology backgrounds, fulfilling our national education policy goal of interdisciplinary education. The program addresses specific gap areas in Indian academia, such as the planetary science and solar physics, which are not currently covered by the standard our qualifying exams. And what we propose is the high-performing toppers from this program are facilitated to attend the National Space Science Symposium, where they will present their innovative ideas on space exploration, integrating them with the professional scientific community. The program prepares students for the technological revolution in space science, space exploration, including digital engineering, AI-driven exploration, advanced material science, and several other disruptive technologies. Aligning with the national education policy's goal for equitable the equitable access, START is also a vehicle to spread awareness about the space science in state-run and rural universities, inspiring the students who might otherwise lack exposure to the space sector. That is also identified as a foundation step for sensitizing the communities to the unique advantage of Bharati Antariksh Station as a platform for microgravity and fundamental science, as well as India's human landing on the moon. The program encourages students to view the growing global space economy as a viable career path, aligning with roadmap goals to increase the private sector participation and play a major role in increasing the space economy of the country. Ample opportunity exists in the space research, and I urge the student community to grab these opportunities to groom themselves into scientists and technologists of excellence, and also as entrepreneurs. I have no doubt that this program will sow the seed for preparing the next generation to take forward our national space exploration endeavors. I wish the participants and coordinate the very best for a successful and enriching START 2026. Thank you, Jai Hind.
Thank you very much, sir, for having elaborated on the significance of this program. And it is my happiness to call upon Kiran Kumar sir, Chair Rapid Science Board ISRO and former Chairman is Secretary DOS for the special remarks. Over to you, sir.
Thank you, Das, and Dr. Narayanan, Chairman ISRO and Secretary Department of Space, and all the directors and participants of this, in a way, unique program, which has started almost 3 years back. This is the 4th edition. The basic idea is to bring space science and technology awareness training using a mechanism which existed through IIRS. And if you look at what has been happening in the last 3 years, it is quite promising that more than 40,000 participants have been there and almost 20,000 registered participants. And then each year there has been a specific theme selected. And it's also interesting to note that AICTE is recognizing this activity, and as a result of that, some of the students could also get some credits in the new NEP program. But basically what is being attempted here is to bring awareness about the space science activities in general. Now, space science itself means observing from space, that is both from space to space and space to Earth also. So in this particular year's theme, It is covering observation from space, looking at many of the topics that are covered, also look at from space to Earth observation. And then because the basic modes of observations and the technological elements used are common, whether you look at Earth or you look at space, except that when you are looking at Earth, only atmosphere is in between, and it could result in many of the observations getting affected. But apart from that, what ISRO has been doing, gradually building the capability of using space technology for doing activities, whether it is Chandrayaan 1, 2, or 3, where you have gone from orbiter to lander. And then in the coming days, you're also looking at sample return and then even landing on moon by 2040. So in all this, there is a tremendous opportunity for enhancing the whole process of observation, not only from near Earth orbits, but also from strategic points, whether you talk of Aditya L1 points or many other orbiting moon or even Venus, etc. So one of the key things we need to appreciate is in India, the country is so large that no matter what of effort we put to bring awareness, it almost looks like a drop in the ocean. So it's very inadequate to reach out to the entire student community across the country. But notwithstanding that, it should be our endeavor to make it happen. And the way this program is configured, also, if you can see, it is reaching out to many centers distributed across the country, and each center with local support, drawing students from those regions and then going ahead. Not only that, participants will also get an opportunity to look at the various programs that are just now, it was pointed out, the last National Space Science Symposium, which was held in Guwahati, Shillong, actually enabled some of the participants of the previous START program to physically come there and participate. So our effort in this particular program is one, to bring awareness and also enable the participation of the younger generation. No matter what discipline they are studying, space science encompasses practically all domains of knowledge and learning. And then, as the technological capability of using, whether you talk about quantum technology or AI or even robotic system creation, etc., in all of them, there is tremendous opportunity. The earlier a person gets engaged in that, their ability to contribute to the program becomes very significant. And in this, I should really compliment both the IIRS and the Space Science Program Officer Headquarters for the initiative they have taken and continue to improve on that. One of the suggestions I have is, while the whatever 26 talks that are being planned and what has happened in the past, also they should make a critical assessment of what they attempted to deliver and whether what they attempted to deliver can be further improved in the coming years. So this kind of introspection is also important, because while we convey information to the listeners, the people who really benefit are those who are conveying, because they learn more than the people who are receiving. And in this, if they have to improve further and do a better job tomorrow, then also need to get in some way assessed in what they are doing. Only then can India go ahead. And if you look at India's position, obviously, as Viksit Bharat, we are talking about, we need to improve and enhance our technological capability, not only technological capability, but also capability of analyzing the information and coming up with inferences, which are very different from what has happened so far. It is only then that the human desire to understand the universe becomes a reality. So in this context, once again, let me compliment all the people involved for doing a wonderful job and wish all the participants of this year a great learning experience. And then your feedback is always welcome, and wish you all a great almost from 11th of March to it's going up to 2nd April. So, and each day it's about 1.5 hours or 2 hours of interaction. So wish you all a great learning process. Thank you.
Thank you. Thank you very much, sir, for this in-depth assessment and giving us action points, showing directions. And we are very happy to request Chairman ISRO Secretary Doers for the inaugural address. Over to you, sir.
Very good afternoon to all of you. Most respected AS Kiran Kumar sir, Chairman Apex Science Board, ISRO, and former Chairman ISRO and Secretary Department of Space, and currently the Space Commission member, directors and directors of ISRO centers and units, Mr. Ganesh Pillai, Scientific Secretary, Mr. Das, Director SPO, and my dear participants, academicians and students. Very, very good afternoon to all of you. It's a good system what is put in place. We are going to have this system on 26 talks are planned. The theme of this year talk is on observation from space. You know, before 1957, the human being were observing the space. And after that, it was 1957, the first man-made satellite Sputnik was placed in orbit. Subsequently, a lot of spacefaring nations, they have placed their satellites for observing from the space. And actually, the topic selected, I could go through. There are 26 topics which it talks about optical payloads, synthetic aperture radar, related aspects, then optics, then astronomy. I think variety of topics are going to be addressed. Now, when you look at, it was 1969 was a very, very important year for us as well as the spacefaring nation. It was 1969, first time man landed successfully on the moon. It was 15th August 1969. Indian Space Research Organization was formed. From that, I think globally as well as in our country, we have grown to greater heights with respect to observation from space. Now, today, if you look at the global picture, I think you all know the recent US after 1969, almost after 55 years, now they are showing interest again to go back, land on moon. The Artemis program is already a very vibrant program. Lot of activities are going on, and there was a accord signed by in 2023, and India is also a signatory to that accord. So that is one part. Another one is if you look at China and Russia, they are leading the show. They wanted to build an international lunar space station, called ILRS. And lunar space station is when we are talking about this type of space station, one is technology development. Second thing is after building lot of science experiment which has to take place. And then like that, globally, one is with respect to this type of activity. Second thing is there are a lot of competition. Today, there was a time only government organizations were globally doing the space activities. Today, you all know, for example, the SpaceX, how much they have come up. It is, they have overtaken all of us, including the reusable launcher. And in fact, last year, we were in Kennedy Space Center. Every alternative day, we could see a launch from our hotel. That is the type of level what is happening. Now, coming to the Indian space program, there are a lot of things are done with respect to science mission. 10 scientific missions are accomplished till today. Recently, we celebrated the AstroSat, 10 years of AstroSat. Now also it is working very well, and we have got XPOSat and Chandrayaan mission, Chandrayaan 1, 2, 3. Actually, lot of scientific discovery we have got through these missions, and Mars orbiter mission, and recent Aditya L1 mission. And India is the fourth country which has successfully placed a satellite to study the sun. And almost 20 terabit data has come out, and we have already rolled out the data. Now, one is when we talk about observation from space, there are two aspects. One is technology related aspect to enable the observation from space, including, of course, launch vehicles are required, then that a lot of payloads, all those aspects. Second thing is the science discoveries. This is very, very important. And now, when you talk about India's Space Vision 2047, today, of course, a country which started with a humble beginning, today we have got the capability to conceive, design, and build our own launches, and conceive, build, and place the satellite in place. Till 50 years back, we are not having that type of capability, but today we have got capability to build the satellites. and we have got the capability to build whatever type of payloads are required. We can build, in fact, probably you all know the optical cameras. Earlier, we used to have cameras to take photographs. The diameter used to be only 1 inch diameter is the lens. And can you imagine cameras, what is getting realized in ISRO? 1.7 meter diameter, almost close to 1 feet thickness. Optics in Bangalore, Leo's lab, this type of cameras are getting built for observing the object from space. And then a lot of activities are happening in the space area. Coming to the science, we are going in a big way. You all know Chandrayaan-3. It was a very grand, successful mission. India is the first country successfully soft landed near South Pole of Moon. Not only soft landed, a lot of discovery. Almost 8 minerals we have discovered. Seismic activities we could understand, and thermal profile we could understand on moon surface. Then electron clouds. So a lot of discoveries have come out. Now we are working on continuation of the Chandrayaan program. Chandrayaan 4, we are going to take sample and bring back. And then Chandrayaan 5, we are going to have heavy lander with long-term missions. Almost Chandrayaan 3, the life was only 14 days. The lander life was 14 days, but here we are talking about 100 days life. And the rover with heavy mass, Chandrayaan 2, 25 kg, here 350 kg. And we are talking about the future program like the Venus orbiter mission to study the Venus. And Mars, we have accomplished the orbiter mission. Now we are working on Mars landing mission. And ExoWorld, this is one of the projects what we are discussing to get the government approval. So there are a lot of interest in the science area. Now the program, what is conceived, the program START, what is conceived, the main idea is to enable the next generation youngsters to have interest on this area and make scientific temper in you, so that you will become the really great leader for building our country. Now, under the visionary leadership of Honorable Prime Minister of India, Narendra Modi ji, today the space, the vision of the space program is rolled out. As Mr. Ganesh Pillai told, we are going to build. Right now, we are working on our Gaganyaan program, and we are planning to send our own Gaganyaan 3s to space and bring them back safely. Maybe in another 2 years time frame. That's what is the target. And we are going to have our own space station, which is going to be built by 2035. And we are working on landing on Indians on moon and bring them back safely by 2040. Already the brainstorming activities are initiated. So there are a lot of activities in the space arena, other than the application related activities to ensure the happiness and safety and ensure that food security, water security, and communication, everything. Other than that, in the science area, a lot of activities are planned. In fact, the 26 topics, my knowledge on this topic is also very, very limited. Given the opportunity, I would be happy to hear all the topics. Everything they have selected in a very, very highly interesting way, starting from optics to astronomy to whatnot, radio astronomy. I think multiple places you are going to get benefit out of it. So really, please make use of this opportunity. These opportunities will not come just like that. Please make use of the opportunity. When we talk about a country economically, we have today with a humble start, we have started in the economic area, and today we have bypassed even Japan and UK, and we have reached the 4th level. And when Honorable Prime Minister and the entire country is working towards the Viksit Bharat 2047 to make our country as a developed country, surely we should not be second to, I mean, as Sarabhai used to say, we are second to none, and we should not be second in any area, including this science area. And thereby, the theme what is selected, observation from space, is really going to be highly beneficial. Through the 26 lectures, you will get benefit out of it. Let me first of all compliment the organizing team. It is not that easy to organize this type of thing, taking this entire activities to close to 10 to 12,000 students. And please enjoy, and you will really get a lot of benefit out of this program. And I hereby declare the 4th edition of START program, START 2026, officially inaugurated. Thank you. Jai Hind.
Thank you very much, sir, for your inspiring words and having declared this event inaugurated. And so this marks the formal closure of the inaugural session, though in another 10 minutes, we are going to have the first lecture, the context lecture of this series, which is on what, why, and how do we observe from space, the context lecture of START 2026. Thank you very much. Jai Hind. In another 10 minutes, we are joining back. Stay tuned.
So first is your lecture,
Yeah.
So your lecture, you please
Good afternoon. I am Praveen Kumar, Deputy Director, Science Program Office at ISRO Headquarters, Bangalore. Welcome all of you to the 4th edition of Space Science and Technology Awareness Training Program, START-2026. As you are aware, this edition's theme is Observation from Space. There are 26 lectures in 5 sessions. In every working day, there will be 2 lectures. Each one is having 45 minutes duration, including question answer. First lecture starts at 3:15 p.m. and second lecture starts at 4 p.m. Date and time of the online test for the participants from the nodal centers will be announced in due course. There will also be a concluding session. Dates will be announced on a later part of the program. Today, we are going to hear the introductory lecture, which is setting the platform for the theme. And the title of the talk is What, Why, and How Do We Observe from Space by Dr. Tirtha Pradeep Das. And I would like to introduce the speaker. Dr. Tirtha Pradeep Das is Director of Science Program Office at ISRO Headquarters, and he is responsible for the programmatic orchestration of all the scientific activities of ISRO's Department of Space, which include the space science missions, building roadmap for scientific exploration, and enabling the scientific community to collectively contribute to the space science exploration program of the country. Spanning a career of 2 decades, Dr. Das has a diverse range of professional experiences, which include launch vehicle integration and testing, HF phased array radar, scientific payload development for sounding rockets and planetary exploration platforms, and most importantly, formulation of spaceborne experiments for planetary missions. In the domain of planetary missions, he is experienced in the fields of scientific formulation, payload development, space qualification, project management, as well as mission operations of scientific payloads. He has participated in all the space science missions of ISRO since Chandrayaan-1 in various scientific, technical, and leadership capacities. His major scientific contributions are in the domain of lunar and Martian neutral exosphere. He has specialized in the domain of spaceborne neutral mass spectrometry. Apart from playing various roles in scientific and technical capacities, he has also played programmatic roles towards the formulation of a set of disruptive technologies for the Indian space program. He also plays significant roles in international cooperation in space exploration as a domain expert and a member of several committees that interface with the global space agencies. Currently, he is engaged in the formulation of space science program of ISRO, scientific community building, and interfacing with the academic institutes of the country. He is also a science communicator. Before inviting the speaker, requesting the participants to post your questions in the chat box so that the speaker will provide the answers at the end of the lecture. Thank you, and may I invite Dr. Das to deliver the talk.
Thank you very much, Dr. Praveen, for this introduction, and very happy to deliver the first lecture, the context lecture of this year's START 2026. What, why, and how do we observe from space? So when we speak about space, it is very interesting to note that there is no universally accepted definition of space. It is customary to speak about an imaginary line over the mean sea level at an altitude of around 100 kilometers, which we call the Kármán line, after the great scientist Theodor von Kármán, who has contributed significantly in the domains of aerodynamics. But this 100-kilometer boundary is not sacrosanct to be qualified as the definition of space. If you see on the Earth's surface near the mean sea level, if you consider a volume, an imaginary volume of 1 meter cube, that volume would contain around 1.1 kg of atoms and molecules. The same 1 meter cube, if you translate to 100 kilometers of altitude, the mass will be around 10 to the power of -7 kilograms of atoms and molecules. So from the surface, when you climb up to the atmosphere and eventually go beyond the atmosphere, the number of atoms and molecules per unit volume, they decrease in an exponential fashion, as I have shown in this slide. And we say that at certain height, the atmosphere becomes so thin that the gas atoms and molecules, they rarely collide with one another. In other words, we say the mean free path between the gas atoms and molecules become very, very large. How large? They can be large as a football ground. If you see on Earth, the mean free path, that is the mean distance traveled by gas atoms and molecules between the successive collisions, is very less. It is in the order of maybe a fraction of micrometer. And just imagine from micrometer, it is going to a few tens of or hundreds of meters when it comes to the mean free path. So that is space in the context. Now, after having understood the basic notion of space, it is important to dive into the topic of today's discussion. Why do we need scientific observations from space? Because when we observe from ground, that is also an option to do the observations through telescopes and big giant antennas which are situated on the ground. But the atmospheric layer which intervenes between the telescope or the antenna and the subject of your interest, they cause a lot of disturbances to the scientific observations. It is something like when you look at the sky, night sky, the stars to twinkle. So when we see the stars twinkle, it is basically the twinkling is happening basically because of the refraction of this light which is coming or passing through the atmospheric layer. So the atmospheric layer not only causes refraction, but it also causes certain frequencies or certain wavelengths of light to get absorbed by the gas atoms and molecules. And there is also a phenomena of scattering of light. Especially you will be able to appreciate when you try to look at the sky from a polluted region with a lot of dust and aerosols, you will not be able to see systems which are of your interest in a better way without the intervention of the atmosphere in between. In between, just wanted to know, am I audible? Is there any issue about the audio?
Now it is okay, fine.
Now it is okay, so I will continue. Okay. So we were discussing about the polluted cities vis-a-vis the pristine mountains. From there, you can see a better sky, a clearer view of the sky. So this is the difference made by a polluted city vis-a-vis a pristine mountain and altitude, wherein you are beyond the realm of so many dust particles and aerosols. You are not really amenable to scattering and all these effects. Now imagine what will happen if we're given access to space where atmosphere is literally not present. 300 kilometers, 400 kilometers, 500 kilometers above the mean sea level. So it is very clear your observations are not getting disturbed by this atmosphere. Now, what happens in certain applications, going beyond the Earth's atmosphere is not enough. Your demand could be not only I shall be beyond Earth's atmosphere, I shall also be beyond the magnetic field of the Earth. As you are aware, Earth has a magnetic field, as I have tried showing in this picture, panel A. The tiny dot you are seeing here, the small disk is the Earth. And around the Earth, there is a magnetic field, which is pushed by the magnetic field of the sun. And there is an elongation effect in the anti-sun direction. So what happens? In the sun-facing phase, the Earth's magnetic field extends up to a distance of around 6 to 10 times of Earth radius. Now, from the sun, whatever the charged particles are coming, they are being emitted from the sun and they're going in the solar system. In between, if you see a magnetic field, this magnetic field is causing this charged particle to get deflected. And that is why we are protected on Earth, because the charged particles of the sun, high energy charged particles, they are not directly hitting us, they're getting deflected by the Earth's magnetic field. Some of them are getting some open paths to the open regions of the Earth's magnetic field and getting precipitated in the polar regions, demonstrating the beautiful, spectacular aurorae. Aurora borealis and aurora australis, that is a different part of the story, but in general, we are protected. So if you want to observe some phenomena which is related to the charged particles coming from sun, going outside the atmosphere is not enough. You have to go outside the Earth's magnetosphere also. Sometimes your requirements could be more stringent. You may say, I want to sit in a position in the space from where I would like to see the sun, observe the sun continuously 24/7 without getting obstructed by anything. Now imagine, to serve this purpose, if you send a satellite around the Earth's orbit, your purpose will not be fulfilled because sometimes the satellite will go behind the Earth and your sun will be eclipsed by the or obscured by the Earth. Instead, if you think of the first Lagrange point in the Sun-Earth system, what is the first Sun-Earth Lagrange point in the system? It is the point, hypothetical point, where the gravitational force of the sun and the gravitational force of the Earth, they get cancelled out. So if you have an orbit around that hypothetical point or the first Lagrange point, you will be able to see the sun continuously without getting hindered by anything else, because as the Earth rotates around the sun-Earth line also rotates, and the Lagrange point also moves along with that. So the relative position of the Lagrange point 1 with respect to the sun and the Earth doesn't change. And this Lagrange point 1 is well beyond the magnetic field of the Earth. So you get a very good chance to see not only the sun, but also the charged particles which are coming from the sun. So because of these reasons, you need to have observations from the space. And I just wanted to convey you, when we say from the space, this itself has so many options, so many complications, and so many technology challenges. So as I started my lecture telling that you could have studied the space from the ground, we do have a lot of ground-based systems. A few of the ground-based systems I have tried showing here: the SODER, sound detection and ranging, different towers measuring atmospheric or meteorological parameters, then multi-wavelength radiometers, then rain gauge, weather radar. All these things are ground-based instruments. There are certain telescopes, giant antennas. But if you want to avoid a major chunk of the Earth's atmosphere and its effects, the first option that is coming to you is the scientific balloons. The scientific balloons can take you to an altitude of around 40 to 50 kilometers and can stay there for some time and allow you to make some scientific observations. But that also may not be sufficient. You may like to go above the common lines and to a bit deeper realms of the space. So you have to take the help of the sounding rockets, which can give you access to around a few hundreds of kilometers altitude from the mean sea level. But there is a disadvantage
associated with the sounding rockets. Sounding rockets does not allow you to make a continuous sustained measurement. It goes, and while it is soaring in the sky, your scientific instrument might take observations, and if you can arrange some mechanism with parachutes system and make your scientific instrument come down under gravity with parachute, you can make some scientific observations like vertical profiling of certain parameters. But there may be some needs of sustained observations from a deeper space, and that is how the satellites and space probes and others come into picture. And for doing all these things, you need a launch vehicle. And I must tell you that all launch vehicles are rockets, but all rockets are not necessarily launch vehicles, because sounding rocket is also science and also in terms of making the living conditions on the earth better. So we can observe the earth. Yes, I can hear something. On the earth better. Yeah, shall I continue? The audio is okay. Yes, I can hear something. You can mute the microphone, those who are not speaking. Yeah, shall I continue? Those who are not speaking.
Yeah, audio is okay.
Audio is okay, so I will continue. So I was discussing about the possibility of Earth observation when you are in the satellite from, let us assume that you are typically around some 400, 500, 600 kilometers above the mean sea level, and you are in a suitable orbit. So you can make use of the visible wavelength region of the light electromagnetic spectrum, which is approximately 400 to 700 nanometer, to take pictures like the way you take a camera or a mobile selfie. Same way you can take a picture from that altitude of the complete Earth, or a part of the Earth at least. So these are used for high resolution urban mapping, disaster management, disaster assessment, and many general planning, like how much land do we use, how much natural resource you use. If you want to classify what is the land use or how much is the urban region, all these things you can do using the optical part of the spectrum. Then you have other parts of the electromagnetic spectrum which you can use to observe the Earth, like you can use microwave remote sensing, or the radar remote sensing, use microwave, and it can penetrate the clouds, smoke, and darkness and provide all weather imaging. And it is vital for monitoring different events like floods under heavy cloud cover. In the heavy cloud cover, your visible light will not penetrate, and measuring sea ice thickness and also several ground deformations using interferometric techniques. And there are also infrared remote sensing. Infrared remote sensing, many of you are aware, it is like the heat signature. During the time of COVID, we had handheld cameras, and people used to see one image of the person, whether the temperature is high or low. So it is basically a thermal camera, different wavelengths we call it, either near infrared or short wave or thermal. They're basically heat signature measurement instruments. And these are the primary tools for measuring temperature variations on the Earth's surface, and which are used for tracking forest fire, volcanic activity, and also whether there is any change happening in the sea surface temperature, which is very important for understanding the climate and the weather. All these things can happen, can be facilitated, and which can help in the policy making also. This is not only important from the point of view of science, but also from the point of view of policy making. Now, after in the right side, I have tried showing two examples. The first one is the example of an image which is taken using a visible camera, and the lower one is in infrared. But as you know, infrared we cannot see with our eyes. Infrared is invisible to human eyes. But if you have to represent what you want to represent of the scientific parameters, you have to make use of a false coloring. It can so happen like if a region is very hot, you may assign some red or orange color. If a region is not that hot, you can assign some color like purple or blue or green. So you are assigning a color, and that is known as the false color composite. Otherwise, you are not able to see infrared with your human eyes. So this false color composite is used in this kind of wavelengths which your eyes cannot see. Then apart from this, you have two different other techniques of observation. One is multispectral imaging, other is hyperspectral imaging. So what happens in multispectral imaging? In multispectral imaging also you're capturing a picture. Imaging means you are taking a picture and it captures this image across a small number of wide discrete spectral bands, maybe in the red filter, green filter, blue filter, or the near infrared filter. There are very handful number of wide spectral regions through which you try taking pictures. So how does it help? It helps because when you want to get or categorize certain information on vegetation, on different aspects of the agriculture, there are certain wavelengths which carry information, and you define a lot of indices based on how much intensity is gathered in the red channel, how much intensity is gathered in the green, blue channels. All this information are available to you to work out certain indices which will tell you about what is the vegetation, what is the quality of vegetation, etc. Hyperspectral imaging is something similar but a bit different, because here there are several hundreds or few tens of hundreds of very narrow contiguous spectral bands across a continuous range. So you can say while multispectral is a discrete set of wavelengths, hyperspectral is almost a continuous range of wavelengths under which you can study a given body. So how does it help? Because it helps because hyperspectral imaging allows you to create a spectral signature of for every pixel, allowing for the identification of specific materials based on their unique chemical composition. And it is essential for mineral exploration and detecting any invasive plant species, monitoring water quality, and this type of techniques are used in exploring other planets as well. Here I have shown you one example. This is also a false color, but spectral cube. Spectral cube is nothing but what you are able to see different wavelength bands. There are numerous number of very narrow wavelength bands forming one set of data over the other. If you take out any slice out of this cube, it will represent how does that scene look in that wavelength, at that wavelength. So it is called a spectral data cube. It is a stack of information of a given space at different wavelengths in a continuous, almost continuous regime. Now, after having spoken about the Earth, if we slightly broaden our perspective, we start speaking about the near Earth space. And in the near Earth space, we start speaking about the sun. And very interestingly, even today, near Earth space doesn't have any definite definition. It also depends on the context. And let us say about the sun and the Earth system, there are several influences coming from the sun: solar radiations, high energy, charged particles from the sun. And when the charged particles move, there is a magnetic field associated. So we call it a solar magnetic field or the interplanetary magnetic field that also comes from the sun. So sun is not only about the light and heat. It is also about the particles. It's also about the fields which are associated with the moving charged particles. And when they come and Earth comes in between, obstructing their flow, they are affecting the upper atmosphere of the Earth. A part of the atmosphere, upper atmosphere gets ionized. And the thermosphere, magnetosphere, they all feel the forcing or the influences of the sun. And this disturbance can be felt by the upper atmosphere, middle atmosphere, And there are a lot of coupling mechanisms between the lower atmosphere, middle to upper atmosphere, and then ionosphere, thermosphere, magnetosphere system, and the sun. So in entirety, this sun-Earth system, it works as a system of several systems. I repeat, it works as a system of several systems. And that is the near Earth space is all about. And sometime in the near Earth space, you have some guests like comets start bothering, because if they hit the Earth, they may be threats. So they're called near Earth objects. Now, if you slightly broaden your perspective a bit further, from the near Earth space, we will go to the solar system bodies. In the solar system bodies, you have, so what do you study? You have planets, natural satellites, comets, small solar system bodies, interplanetary dust. So you can study the material composition, what they are made of. You can study the surface, and you can study what is below the surface, the subsurface. You can study the atmosphere, if there is some atmosphere. So what will you study in the atmosphere? You can study the density of the atmosphere. Density means how many atoms or molecules are there per unit volume. That is called the density. Composition of the atmosphere, you can study whether there is any dynamics in the atmosphere, transport in the atmosphere. And with respect to all this, you can compare between the planets. What are the similarities and dissimilarities between Earth and Venus, Venus and Mars, Mars and Mercury, Mercury and Moon? So planets not necessarily should be planet, anything in the solar system. So that is comparative planetology. From there, we understand, despite the fact that everything started together, Moon, Venus, Earth, Jupiter, everything started together, their journey, but today they are different. How they have evolved over time, how the differences were made between them, this is the subject of comparative planetology, like we speak about comparative literature today. Then another topic is sun-planet interaction. Depending on their differences, how sun will interact with different planets, that also differs. The way sun interacts with the moon is not the same way it interacts with the Earth, or it is not the same way it interacts with Mars or Venus. So sun-planet interaction is very closely connected with the comparative planetology, and that's how this kind of study, material composition, etc., we have to do. Now, you might think that there is nothing beyond that, but that's not correct. Even wherever there is a void, nothingness, no planets, no artificial, no natural satellites, still you have certain things to study. Like you can always study the charged particles which are coming from the sun. Most of them are singly ionized hydrogen or doubly ionized helium. They could be a subject of interest. Or you can also study the interplanetary medium itself. In the interplanetary medium, there are different entities for study. One is solar wind. You can also study the interplanetary magnetic field itself. You can study the interplanetary dust particles, okay, cosmic rays. They're small, tiny objects, entities in the solar system, but those are also telling certain physics about the origin and evolution of the solar system. Then again, if you start expanding your perspective beyond, then you come to the realm of astronomy, astrophysics, astrochemistry, cosmology. So what is astronomy? Astronomy is the study of the stellar objects. Astrophysics is the study of different physical processes in those stellar objects. Today we speak astronomy and astrophysics. Together we speak, right? We cannot distinguish between astronomy and astrophysics. It is correct because the way we cannot distinguish the luminosity of a candle flame from its heat, you may not be able to distinguish between astronomy and astrophysics. But the subtle difference is astrophysics tells about the physical processes in those stellar objects. In similar lines, there is astrochemistry, wherein you study the chemical processes in the stellar objects. And astrochemistry studies give you a lot of clues about the concept of life, how life has formed in the Earth, or whether life could be there in some other planets, in some other exoplanets, in some other solar system, astrochemistry will tell how the basic building blocks of life started. And then we have cosmology. So cosmology is very, very interesting. It studies the bigger picture, still bigger picture in space and time, even before the stars and galaxies were born. So I give you it an exercise that find out, did the stars and galaxies form immediately after the creation of the universe? If not, what existed then? So all that I want to say is, if you say universe started around 14.6 or whatever billion years ago, and the fast formation of stars and galaxies, which are the subject matters of today's astronomy, did those start right in the beginning along with the start of the universe? If it is not correct, then the period in which universe started but the stars and galaxies didn't form, what was there? Okay. So when you see this subject in the totality, it becomes cosmology. So just to summarize, we started from Earth, we started from the Earth observation, and then slowly we have built upon and we have gone to the realms of the solar system and beyond the solar system and the astronomy, astrophysics, cosmology. Now, how do we study these different celestial bodies and the processes? So in general, you might ask me a question, what do you study? So if I have to summarize, what do you study? Part of the lecture, we study different celestial bodies. We may study their physics, their chemistry, and we may study different processes which are happening in this space. Okay. Now, how do we study? We take help of certain platforms for exploration. We may take the help of some satellites which are around the Earth or any other celestial body. There could be landers landing on some planet or some natural satellite. That way we have landed the Chandrayaan-3 on the moon, or impactor, like the way we have sent the moon impact probe in the first Chandrayaan mission, 2008. We can land rovers, like the way we have made the Pragyan rover rove on the moon surface. Then we have flyby missions, wherein a spacecraft passes close by a celestial body and conducts scientific observation. So here I have given one example. It is an artistic view of the Cassini spacecraft during the Titan flyby. Then you can have space observatories, which are launched to space to observe celestial bodies and astronomical sources. Here I have shown the example of the Aditya L1 Solar Observatory of India. You can see the Earth, you can see the Sun, and in between, about 1.5 million kilometers away from the Earth, around the L1 point, there is a different kind of orbit along which Aditya L1 is stationed, and it is looking at the Sun. And there could be some exotic, different, unconventional types of platforms like helicopters. As you know, the Ingenuity helicopter has been demonstrated on the Mars, which was attached to the underside of the Perseverance rover. You can think of many other platforms also. Why don't you think of some platform which will look like some snake? Suppose you imagine a robot which looks like a snake, which can penetrate, and over the face of the snake, you can attach some sensors, some cameras, or some ultrasonic devices, or some in situ observation instruments, and make it go down, take the data and come back. Can you not think of those kinds of instruments? These are all wild ideas. You can definitely work on those. Now, when it comes to the orbits, some satellites, when we speak specifically about as a very much proven platform, you can, what all the things come to your mind? You think of the Kepler's law. In practice, orbits are tailored to meet the scientific requirements of the mission. You have different types of orbits. You are having an orbit like the geostationary orbit, about 36,000 kilometers above the mean sea level. And for the persistent stare on the Earth, okay, Earth is rotating, and with the same angular velocity, that satellite is also rotating. Basically, the sub-satellite point is fixed. So if you draw a straight line, an imaginary line from the satellite to the center of the Earth, and the line cuts somewhere on the surface of the Earth, that is called the sub-satellite point. A geostationary satellite, that sub-satellite point never changes. The satellite would appear stationary with respect to the observer. So which is very good for the continuous weather monitoring and communication applications. On the other hand, you have polar orbits or sun-synchronous orbit. Sun-synchronous orbits are very interesting. What happens in the sun-synchronous orbit? You pass through a region. Say, let us take an example over the Indian region. Say at 12 o'clock in the noontime. Next occasion also, Earth also will rotate. That also will rotate, and it will come back over India again at 12 noon. So that is synchronized with respect to the Earth, to the Sun, and the same local time is maintained for the revisit of the satellite over a given location. That is a sun synchronous orbit. That is a bit offset by with respect to a certain degrees from a polar orbit. Polar orbit is very good because if you have a polar orbit, perfectly polar orbit, 90-degree inclination, you have a good coverage of the sphere of the Earth. You are making use of the Earth's axial rotation and the satellite rotation and covering the Earth in its entirety. These are all Keplerian orbits. They follow Kepler's laws. But there is another family of orbits which are non-Keplerian. Non-Keplerian orbit means these orbits are not contained in a plane of paper. Keplerian orbits can be drawn on a piece of paper, but non-Keplerian orbits are not contained in a two-dimensional plane because in this case, it is a three-body problem. Take the example of Aditya L1. Here I have shown the Aditya L1 spacecraft itself is one body, Sun is one body, Earth is another body. So it is a three-body problem, wherein in the Keplerian orbits you deal with a two-body problem. The satellite itself at the central body, but this is different. Still different is another kind of orbitability that is a bit unconventional and exotic. Out of the ecliptic orbit. Out of the ecliptic orbit, what happens? You are going out of the ecliptic plane. So what is the ecliptic plane? Ecliptic plane is the plane of the orbit of Earth around the Sun. And if you see the solar system from a distance, you will be able to see that there is not much of a deviation of the planes of the other planets' orbits around the Sun. All of them are contained within a small band. All of them you can approximate as coplanar. So that is called the ecliptic plane. Now, there may be requirements you would like to see the poles of the Sun. You want to understand the Sun and you want to see the poles of the Sun, how things are happening. How do you see? You have to design an orbit which is highly inclined with respect to the ecliptic plane. So one such example is the Solar Orbiter, which is a ISRO-NASA joint mission and which was launched in 2020. It used repeated gravity assists from Venus to gradually step up its orbital inclination. It didn't happen all of a sudden. With steps, it was increasing its inclination away from the ecliptic plane. So as of early 2026, the spacecraft has already performed its first high latitude passes. In March 2025, it was around 17 degrees, and now in the future, it is targeting 33 degrees. And I'm sure in future, this technology also will be improved and we will be able to achieve much higher inclination with respect to the ecliptic plane. Now, after having understood the orbits, from the orbits, what do? You can do certain experiments or observations. And that is the objective of today's lecture. That is, how do you observe from space? You need scientific instruments. Scientific instruments or the scientific payloads are the ones which can go beyond the capacity of your eyes or ears or any other sense organ. Your eyes have a limitation. You cannot see wavelengths beyond 400 to 700 nanometer. Your ears cannot hear beyond your 20 hertz to 20 kilohertz. Then these scientific instruments are designed with special kinds of detectors which can sense the signal which is otherwise not possible for any human being to recognize. And having understood this, these instruments are operated in two different ways, or to say in a different terms, these observations can be classified into two broad classes. One is remote sensing, which is the science of observing the subject of interest from a distance, and in situ observations wherein you make direct measurements at the location. So how do you put an analogy? If you look at the cake from afar, you can see the structure of the cake, the color of the cake. You can make an inference from the smell or the color that it is a chocolate cake. But when you go to the cake and take a piece of it and put it in your mouth, you take the taste, then you can tell, okay, really there is a mix of chocolate and the butterscotch or caramel. You can tell the composition, right? So that is in situ. So I have tried showing some example here. The figure 1 is the remote sensing of the moon from an orbiter, our own mission, you can recognize. And figure 2 is the in situ studies of the moon from a lander. You can see the iconic picture of the Chandrayaan-3 lander. So it had some instruments which were taking observations with physical contact of the moon surface, or the atoms and molecules of the ions which are in the vicinity of the moon surface. And you can see also the rover, which also had some instruments which were directly having access to the lunar soil to make some analysis. So these are in situ. So remote sensing, if I speak about remote sensing, mostly this instrument use electromagnetic radiation, visible, radio waves, infrared, ultraviolet, etc. And there are two basic subcategories of the remote sensing. One is active remote sensing, another one is passive remote sensing. In active remote sensing, you have a source of electromagnetic radiation or some source on the satellite, and you are shining the electromagnetic radiation on the subject of interest. And the light which is coming out of that surface, maybe by scattering or by reflection, whatever it is, you are analyzing the reflected or scattered light, and you are making some scientific inference about the subject of interest. That is active remote sensing. That is as if you are having a torch in a dark place, and shining the torch, you are able to see whatever you are able to see. In contrary, there is another kind of remote sensing which is known as the passive remote sensing. In passive remote sensing, you don't carry any source of electromagnetic radiation. You just look. Whatever radiation or messenger coming out of the source on its own, you analyzing that only. So it is just look. Active remote sensing was shine and look. Then I was speaking about the electromagnetic spectrum. Now you see, you just go to a bit better depth. There are different parts of the electromagnetic spectrum. You have starting from the radio waves and microwaves. They are big wavelength, long wavelength signals. The wavelengths could be as big as a few centimeters to even kilometer, like a mountain. Big long wavelength radio waves. Shrink the wavelengths a bit, you get infrared. Shrink it further, 400 to 700 nanometer, the visible wavelength range which human eye can see. Shrink them further, you go to the realm of 10 nanometer to 400 nanometer, you get the ultraviolet. There are also subdivisions. I'm not going to the subdivisions. I'm just telling a broad classification of the electromagnetic spectrum. Then you can go to the realms of X-rays and gamma rays. Now you see here in the second and the third column, I will not go to that details. I just want to give you an impression that how different parts of the electromagnetic spectrum are used for what kind of study. Say, take anything arbitrarily. Infrared part of the electromagnetic spectrum in planetary science can be used for surface mineralogy, greenhouse gas concentrations, and any internal heat leakage from the gas giants, whatever this you can study. But in the astronomy and cosmology, you can study distant redshifted galaxies, the protostars hidden behind the dust and the atmosphere of the exoplanets. So different parts of the electromagnetic spectrum have different stories to tell about a given body. And that is the importance of, if you remember what I told in the beginning of my lecture, the ingenuity of having different parts of the electromagnetic radiation being used to look at a given body, and then take the story which is told by each part of the electromagnetic spectrum, combine the story and build the entire novel about that subject of interest. Then coming back to remote sensing, you have different instruments like imaging, you have cameras, invisible or infrared or ultraviolet, you have spectroscopy measurements wherein you identify the different wavelengths which are coming from a mixture of wavelengths. You have radars, you have radiometry wherein you are measuring the intensity of the thermal radiation. So there are pros and cons of the remote sensing. What are the pros? Pros are it gives you a wide coverage and global view of the subject. They are safer and less resource intensive than landing, can observe extreme or hazard environments. When you see the cons, that indirect measurements relies on interpretation and limited spatial resolution. Finer details can be missed if you do a remote sensing. Effects of the intervening medium. So if there is a medium intervening, like an atmosphere or some field, your observation may have to be corrected with respect to those properties of the medium. Now, let me tell you something also very important. Don't remain under the impression that when you are doing kind of a remote sensing, it is only the electromagnetic radiation which is used for remote sensing. So electromagnetic radiation is not the only messenger that carry information from a celestial body. But from the electromagnetic radiation itself, let us see what more you can do. As I mentioned, you can do spectroscopy. In the spectroscopy, you analyze the different wavelengths which are coming, and you know different phenomena which are happening in the body of interest. You can tell from the spectroscopy. Timing means if this body fluctuates in intensity of the electromagnetic radiation, that contains some information which is known as the timing information. Polarization is another property wherein the electromagnetic wave, when the electromagnetic wave, it is comprising an electric field vector and the magnetic field vector with orthogonal configuration, and there is a forward motion of the electromagnetic waves. So for a given packet of the electromagnetic wave train, the direction of the electric field is the direction of the polarization. That tells whether the polarization is statistically significant or the angle of polarization is undergoing a change. This thing tells a lot of things about, especially the magnetic processes or the magnetic properties of the body of interest or the medium through which the light is coming. Imaging, everybody understands, is the kind of camera. You can take pictures in different wavelengths. Apart from this, you have other messengers also. You have gravitational waves, which are the ripples in space-time generated by accelerating massive objects like black holes and neutron stars, and they provide information about the events that are invisible to light. And gravitational waves you can compare. If you have gone to a children's park, there is a thing called trampoline. So a big membrane, circular membrane, and kids jump on that. And what happens when the kids jump on that? The disturbance is propagated radially. So same thing happens. Imagine the trampoline surface is nothing but the space-time mesh, space-time continuum, and that gets disturbed as information is carried whenever such an energetic phenomena happens in space. And then we have neutrinos, which are subatomic particles that interact very weakly with matter. They can travel vast distances unimpeded, carrying information from the course of violent events. And also we have cosmic rays, which are high energy particles that bombard the Earth from space. Thus cosmic rays can come from the sun. Some of the cosmic rays can come from the extragalactic, galactic origins. They call GCRs, galactic cosmic rays. So electromagnetic radiation is not the only way of understanding any celestial body or the process. It is a different kind of remote sensing, unconventional remote sensing. Coming to in situ, it involves direct physical measurements taken at the location of interest. basic principle is the instruments are physically placed on or within the target environment. Sensors directly interact with the local environment. As for example, if you imagine a seismograph, which is measuring the ground vibration that can work in contact with the surface. That is an example of the in situ observation. And there are some pros and cons. If you see the pros, in situ observations give you direct and unambiguous measurements. Then you have high spatial resolution, detailed local information, can discover unexpected local phenomena which can get missed if you do remote sensing from a distance, because you lose the details when you are doing remote sensing. Cons of in situ observations include limited spatial coverage, because only one part you are going to see, you are missing the totality. High cost and risk, landing, deployment, and operational challenges are also quite significant, because sometimes you may have to land in harsh environments. Now let us assume that you have understood the different kinds of orbits and different kinds of instruments. You have understood the classification of in situ and remote sensing observations. Now, what do you gather by these observations? You gather some data. And this data are some physical parameters, information. It could be temperature, pressure, or ground vibration, something like that, some physical parameter. And those parameters have to come to the scientist who's sitting in the ground station. So here I have shown a picture of a ground station where scientists are sitting. So what happens? Signals are generated in the satellite or a lander or a rover, whatever it is. In this picture, I have shown it as a satellite. It could be lander, it could be a robot also. There are different scientific payloads. Either they are doing remote sensing or in situ. They're gathering certain information, that the information has to come to the deep space network. So how these things happen, let us see, have a closer look. Step one, the birth of the signal. The data are acquired from the sensors, which are also known as the transducers. What happens? The physical quantities are converted to electrical signals. In most of the cases, in general, it will not be wrong if I make a statement. In general, they are made voltage. Even if a current is generated by some physical phenomena in the sensor, the current is also made to pass through a resistor, and by Ohm's law, you have V is equal to IR. The voltage drop across that resistor becomes an electrical signal against whatever you are measuring. You are measuring temperature, pressure, humidity, your particle flux, light flux, magnetic field. At the end of the day, it becomes a voltage, analog voltage in a range. Now, this analog voltage is converted to a digital signal, and there is a kind of a processing. In the processing, you can make a proper formatting, because you have to transfer this data in a well-defined format. You can do all this formatting. Sometimes people do a certain kind of calibration also on board. Certain value addition or compression of the data also are done in certain cases in the onboard. Sometimes filtering is done to strip off the signal noise. All these things are coming under the premises of onboard processing. Okay, now you are ready for transmitting. So what happens? You have all this data, processed data, in a queue, in the transmission queue. And this onboard data management process involves processed data packets are temporarily housed in the solid state devices. As the bandwidth is limited, data are strictly prioritized, and critical engineering, health matrices, and high priority science observations are flagged to skip the line. So certain important parameters are there, they can skip the line. This is a kind of an asynchronous transfer, and then you feed it to the baseband system of the platform, which contains an antenna, and you have a process of modulation with an electromagnetic wave, and the electromagnetic wave, nests the digital signal packets, and it is transmitted to the ground station. Now, what happens at the ground station? You receive the signals and do a demodulation, because a lot of different sensors data have been mixed. We call this process multiplexing. We do multiplexing and then we do modulation. And when we receive, we do a demodulation and demultiplexing. And payload-wise data we can segregate. Okay. If there are 10 payloads in a mission, payload means scientific instruments. If there are 10 payloads in a mission, all these 10 data outputs can be streamed out in the process of demultiplexing. And then we call them raw data. And these raw data are analyzed with respect to something called SPICE. So what is the SPICE? We will see what is the SPICE. So let me tell you, SPICE is a system which provides the exact observation geometry at the moment when this scientific observation was done. It is not important to know only the physical processes which are happening of a celestial body. It is also equally important to know when you have taken the data, where you were in the orbit, where exactly you were pointing, what was the time, what are the geometrical parameters. So these are all called contextual information. If you don't know the contextual information, your data analysis will be incomplete. You will be able to tell, I was smelling a rose garden, but you will not be able to tell exactly where you have marked a garden of roses. Okay, so SPICEs are a set of computer programs which help you to add meaning to the scientific information which you have got in the process of acquiring them using the different sensors and transducers. And then you mark this information to get the solution of the data. And there are different levels of data. Level 0, then level 1 could be with some calibration parameters. Level 2 maybe with some corrections or some further addition of information. There are different definitions of levels of data. Okay, the raw data usually is called the level 0 data. Level 1, level 2, etc. It also depends on the particular type of instrument you are speaking about. A bit more about SPICE. This SPICE is basically a geometry engine for space mission. It is developed by the Navigation and Ancillary Information Facility, Jet Propulsion Lab, NAIF, and SPICE is the acronym for spacecraft, planet, instrument, C matrix or camera matrix events, SPICE. And this SPICE tells you where, when, and how these observations were made, how to use them. Maybe in very crisply, I can tell you before I conclude my lecture. When you have started learning your computer, any computer program, whatever you have learned about two things. One is the user-defined functions and the library functions. In the user-defined functions, you could write some function and call those functions in your program subroutines. On the other hand, there are some library functions which came with the software package itself. You don't know what is there inside, but you call them. It has got a definition of input and it has a well-defined output. So there are many library functions in a computer language. SPICE package is also something like different library functions, which we call the kernels, which are giving you some contextual information. Some tell you about angle, some tell you about the time, some tell you about the location. All these things you call as per the need, and you build the total information about the celestial body. Okay, and then after having this, you archive your space science data, and there is a process of long-term preservation and accessibility. Spaceborne data are unique, irreplaceable asset, often acquired at immense cost and effort. So there should be a long-term archival, which called it LTA. Okay, and this process has got certain philosophy, like it should have a definite format, standardized format, so that anybody from any part of the globe can access and make sense of it. Generation wise, you can go on using it. So there are certain discipline and well-laid plan to achieve this long-term archival LTA. As I was mentioning, standardization, effective archives mandate standardized data formats like FIDS is for astronomy, then NetSDF or HDF for earth science. You have PDS or planetary data systems for planetary science. And also there is a concept of metadata, which is data about the data. It's very critical because sometimes you tell I want data on this part of the moon. Okay, that becomes your metadata. What is there inside? That is the actual data. So data label definitions are also coming. What do you mean by level 0, level 1, etc. And there are documentation file with some caveats. If there is a mistake or something, you have to take with a pinch of salt. All this information are there in the caveat. All these things form the archival. And for your information, this is the website where you will be able to get and access Indian space science data. And this is free of cost. The students are urged to go there, and all you need is a valid email ID and access. Start using this. So I summarize this lecture, and what did I speak today? I spoke about what is space and why space. I spoke about different techniques and platforms. I classified between remote sensing and in situ, compared between them, and I also told about multi-messenger approach, and also spoke about why raw data alone is not sufficient, the importance of the contextual information and spice, and also I went to the data levels and archival. So with this, I conclude my presentation, and I unshare my presentation so that I can see all of you, and maybe whatever 5 minutes I have, or if there is any question, Dr. Praveen, I can tell. Thank you very much.
Thank you, Dr. Das, for a wonderful lecture. You have covered almost all the why we have to go to space to observe the stellar bodies. So it has covered what, why, and how do we go for the space observations. And you have already set the context for the future lectures as well. Now we will see some of the questions from the chat box. Yeah, one of the interesting question is, when should a mission prioritize in situ observations over remote sensing?
Okay, that depends on the scientific need. I will tell you, when we have discussed about the different pros and cons of remote sensing and in situ observations, I spoke that remote sensing is very good when you are trying to cover the entirety of the physical body, like you are trying to cover the entire moon, and that is your objective. So in that case, your option is to have a remote sensing observation. On the other hand, if your objective is to be specific at a given location of the moon to see what is happening, then you have to have an in situ observation by a physical contact to that part of the moon or any celestial body. So in this process, you lose the picture of totality when you are going to in situ. Okay, but you are gaining the direct details wherein there is no other intervening media which might have caused some error in your interpretation. So it all depends on the kind of interpretation you want to make of the body of interest and how much you want to cover with how much details. And also another important aspect, in some cases, it is very hazardous to land on some planet. Let us take the example of Venus. So the hostile environment of Venus cannot allow any subsystem or any lander to have sustained observation from the surface of Venus. First of all, it is having a thick layer of atmosphere, then cloud system. And even though you were able to make something land and stay on the surface, it might die en route. So in those case of hostile environments, what do you have? You have the option of remote sensing only. Or if you want to study a distant planet, suppose you are trying to study an exoplanet, which is beyond this our own solar system. So you cannot access that, or due to the technology limitations, you are not able to access a very distant outer planet. You have to do remote sensing kind of technique only. So this is how you have to make a judicial understanding of when do you have to choose remote sensing and in situ observation. So I hope it is clear.
Okay. Thank you, Dr. Das, for this information and no, very nice reply. Okay, the other interesting question is why we can't simply launch a telescope to a very high orbit, say 50,000 kilometers, instead of placing it at a Lagrange point?
Okay, if you can place an orbit at 50,000 kilometers, that you can do. But in my lecture, I have mentioned about the features or uniqueness of the Lagrange point. In fact, there are 5 Lagrange points for a two-body system. In my lecture, I have restricted to only one Lagrange point for the sake of understanding and brevity, with Lagrange point 1 in the Sun-Earth system. Let us assume you have told about something having sent at 50,000 kilometers. At 50,000 kilometers, you can definitely have some orbit, but that orbit might not fulfill or will not fulfill the needs which are fulfilled by of the first Lagrange point. The first Lagrange point's need is to be stationary in the Sun-Earth joining line, have a continuous stare at the sun, sitting outside the Earth's magnetic field. If you say 50,000 kilometers, let us take an example. If you take the diameter of the Earth around 6,000, sorry, the radius around 6,000, it becomes around 8 times. So you are still within the magnetosphere. You cannot go outside, but Lagrange point 1 is outside the magnetosphere of the Earth. So this thing you cannot compare in terms of the requirement of orbit for any scientific objective. So I hope this makes sense.
Maybe one last question. Why is a 400 kilometer sighted as a sufficient altitude for space observation when the atmosphere is much thinner at lower heights?
It is correct that atmosphere is thinner, but it so happens, although we speak of a thinner atmosphere even from 30, 40, 50 kilometers also, atmosphere gets substantially thin. But still, if you see at even 150 kilometers, 200 kilometers, 250, 300 kilometers also, atmospheric density doesn't become zero. Atmospheric density remains. Collision between the atoms and molecules might be rare, but you cannot deny that they are still there, maybe less in number. So what happens if you launch a satellite at a lower altitude, suppose 200 kilometers, let us see, or 150 kilometers, although substantial atmosphere is not there, but whatever gas atoms and molecules are there, they can interfere with the projected area of the satellite and cause enough drag of the satellite. So you know that the force of the drag, you have a drag coefficient, you have the multiplication of the dynamic pressure, half rho v square. V is the velocity of the satellite and rho is the number density multiplied by this drag coefficient. It gives you the force. So at lower altitudes, this kind of a problem is very significant, wherein satellite orbits are not stable. It will have to do a lot of station keeping to maintain the orbit. If you don't do, the atmospheric drag will make it have a spiral trajectory, and eventually the satellite will come down. Now there is another problem. When the sun becomes active, the atmosphere, the upper atmosphere or the atmosphere itself expands. And when to be specific, the thermosphere expands, even if you place a satellite at 400 kilometers, those satellites also can start feeling the drag, which may not be the case otherwise in the cases when sun is not that active, quiet sun period. You might recall in a few weeks ago, SpaceX, these agencies have lost several of their satellites because of the solar activities. Thermosphere expanded And because of the expansion of the thermosphere, these satellites we should not have faced any drag otherwise, they have started facing drag, and problem happened. So these altitudes, 400 kilometers is nothing sacrosanct, but this kind of concept is there that higher you place, it is better. But you have to also remember from the Kepler's law, if you are placing a satellite very close, your orbital velocity has to be very high to make it stable. Then you make it a bit higher, then a bit slower. Okay, that comes from the gravitational laws. At the same time, you have to see how your revisit time, your spatial resolution, coverage, drag, all these things tell at what altitude you have to place a satellite. That's how a mission is designed. And that gives you the answer why 400 kilometers and why not below 400 kilometers. Thank you.
Thank you, Dr. Das, for a very nice explanation. Due to paucity of time, we can't take up more questions here. So the thing is that what are our questions raised by these candidates posted in chat box as well as in YouTube? We will collect it and put it in one place, and we will see how well we can answer all those questions. Okay, so with this, we are concluding today's session, and we will be meeting tomorrow just at 3:50. There will be 2 lectures, 45 minutes each duration. And so we will meet again tomorrow. Thank you all.
Thank you. Thank you very much. Bye-bye.
Yeah, thank you, sir.